office, or we need to take one of them. Lower the volume.
Any better?
Is that good? You like that? All right. So we're trying to video these this year. All right, well, let's get started. Thank you, everybody, for coming. All right, so this is, I thought this was the only tutorial I was going to be giving, and then poor Hassan Zouani, Professor Zouani from France, emailed me yesterday, and they have a family emergency. His mother passed away, so I'll be giving 3 tutorials tomorrow, as it turns out, because he was going to give 2, which I think would have been excellent. But anyway, so I thought I would start off to give you some of my thoughts on what the basics are of surface metrology in a more general kind of sense. And let's... There we go. Whoops. All right, now we're moving here. We'll go back. All right. Okay. So one of the interesting things is we talk about roughness, and lots of people talk about it. And it's one of the sort of common words that we use in everyday English. What do we mean by it? And it gets more interesting in a technical sense, and as the chair of the committee that writes the standards on this, it's interesting to sort of take a look and see what our concepts are. So we want to talk about what roughness is. Of course, this is about metrology, so I want to cover some basics on measurement, and then analysis, and just a little bit on the value that we get from surface metrology from an engineering perspective, but because in engineering we're often trying to put dollar values on things. That's one of the reasons it's so much fun to work with the anthropologists and archaeologists, because the perspective is so much different on sort of what creates value. Engineering, it's sort of bottom line. So here's some questions. As we look at sort of geometry, we start off with sort of large shapes, and we tend to define those in Euclidean space. So when an engineer is designing something, they're generally designing things like cylinders and planes, but then as we get to the finer scales, things start looking more chaotic. So as we go from dimensional, what we call dimensional metrology, where we're saying sort of what's the diameter of this ball bearing, to surface metrology, where we're saying what's the roughness on this, there's actually a continuum of geometries, but we parse it up in special ways. And how do we get there? Well, the processes that form some of the surfaces at a very fine scale and we had a discussion about this at the ISO meeting a couple weeks ago, are they deterministic or non-deterministic? And that gets into some of the fractal things. And so if we could set up a machine tool and the workpiece and everything exactly the same way twice, there's a theory that says you'd get exactly the same surface roughness, but you can't get it set up the same way twice, so it's kind of a moot point. But so the processes, according to some of the current theories, like Jim Bryan, are deterministic. But the challenging thing is it's like the butterfly effect. You'll just never line up everything to get the same effect another time. Now, and here's an interesting thing too, and we'll be looking at how we drive sort of in manufacturing Euclidean geometries down to finer and finer scales. So what would we want at a very fine scale if we could actually design it in Euclidean space? Right now we're kind of stuck looking at fine scale stuff as statistically somehow. And so I posed this question actually to an engineer from Daimler-Benz. I said, suppose you made a very nice car and you could design the cylinder liner down to the finest scale you wanted to in Euclidean space. Would you know how to do it? Because we've been adapting, so we're going to grind it and then hone it, and sort of the current way of doing it. And I said, would you know what you really wanted down to, say, tens of hundreds of nanometers in the interior of a cylinder if you could design it all, put everything in there? And we don't really. So as we look at this, here's a machined surface, and we'll talk a little bit more about the way we model this. But so this is taken off a cylinder, and I probably should have put a cylinder in here so you could see, but everybody knows what a cylinder looks like. So it's turned as a cylinder, and here's where the tool is passed. We can see ridges between the tool marks, and inside the tool marks we see all these scratches. So the surface is distinctly non-Euclidean. There's a little burr there, and so where is roughness in this, and what do we start calling roughness? Well, the roughness is, or the fine scale, let's say the fine scale, influences a lot of different properties, and we'll take a look at those. And so it's important for behavior, things like adhesion and friction, heat and mass transfer. Jamal was just talking about this drying project. How fast something can dry depends on how much surface area you have to transport the liquid out of it. And so these things are down at the scale of roughness. And so we'll take a look sort of current and future. So why is there roughness? Well, this is one of my favorite lines, and I thought it came from the musical, the 60s musical, Their Hair, and I have never been able to find it. So if anybody knows what the reference for surfaces cover everything, let me know. I'd love to find it, but I did not invent that. I heard it someplace else, and I can't remember where I got it. And when we do manufacturing, what we're trying to do is get mechanical parts, and actually other parts as well, try to get the surface we want with the properties, also geometrical properties that we want, where we want it. So manufacturing is largely about surfaces. But one of the problems in manufacturing is that the kinds of things we do, like grinding, and we'll be taking a look at some grinding media in a moment, are inherently chaotic or have chaotic components. So who decides in engineering what roughness is? Well, the designer gets to decide something when they're designing it, and we'll talk about some of the opportunities that are there in doing better designing. Manufacturing, I've been mentioning. And if it's measured with a surface metrology instrument, it must be roughness. So why is there roughness? In a certain sense, well, because we can't chase the Euclidean geometry down to the finest scales. And so it's sort of our limits of surface creation in manufacturing. So, but where is it valuable? Actually, we use roughness to help make seals better, to help lubricate surfaces, friction, aesthetics, cleanability. And this is not intended to be a comprehensive list, or exhaustive list, but it's just to make us think of lots of different behaviors or performances that are dependent on the surface roughness. So as I was saying, we tend to design first in Euclidean space with spheres and cylinders and planes. And then the designer, though, gets to put on the print something about the roughness that they want. Now, and so there's different ways of representing that. So you put here something about here's the roughness, and then here's some indication of the way we're going to calculate the roughness. Let's take a look at more detail on this. So, let's see, the pointer part of this is working. All right, so basically, if somebody says roughness and they don't tell you any more about it, whether or not they know it, they probably mean RA, the average roughness. And that goes here in this position in this traditional kind of indication. Now the interesting thing, because I'm going to be talking more about scale and the importance of scales, and this roughness cutoff sampling length lets you know what the scale is where the designer intends that roughness begins, because this indicates at what scale you decide, all right, so the waviness stops and roughness begins. So this is part of the delineator between form, large scale, dimensional metrology, and finer scale surface metrology. Interestingly enough, this is often overlooked or forgotten. And as we switch from tracing lengths to tracing 2D kind of profiles to what we call 3D surfaces in metrology, or physicists we call 2D, where we've got heights as x in x and y. then the lengths all become different. So anyway, here's the average roughness. I mentioned waviness briefly. So we've talked about form, and that's pretty clear. That's how you're designing stuff. Roughness is the fine scale. But somehow to get in between these two, we have waviness to transition us to get from the fine scale roughness. So this is kind of where we put the stuff that's more difficult to describe in some ways. There's also the lay or directionality on the surface. So here's that machined surface I showed you before. And in the direction the tool went, there's an obvious kind of directionality. And of course, that's important for properties and makes a big difference. If I have a seal that's trying to run this way, it's going to leak a lot. If I have one that's trying to run this way, then it's going to be better. So here's a visual example. This is a cylinder that's been machined. I'll be saying more about this tomorrow, this particular part. So if we take out the form, here's the form, there's the roughness, and in between is the waviness. So this is a kind of geometrical decomposition. Now, historically, the way this has been done and the way we measure it really is very dependent on use in the car industry, which has driven this. But as we get into other things like microelectronics, the same sorts of cutoffs between form, waviness, and roughness are not going to be so effective. And we need to look at more general ways of describing the scale at which roughness starts based on some other things. Now, from an engineering standpoint, we would like to know this kind of relationship. In other words, if I change the roughness, how does it influence the performance? And when I'm designing something, I'd like to be able to say, all right, here's the performance tolerance I want and the way the thing functions. And then I know this is the relationship between the performance and the roughness, so I can go over here and say, well, here's my roughness tolerance, and I can spec the roughness that way. Now, that would be the ideal way of doing it. So I know we've got some practicing engineers in here. And do we have anybody that specs roughness in here in design work? How many of you do it this way? Would you like to do it this way if you could? Yeah, I know when I was giving a talk in Detroit a few years ago, I said, I suspect the way you spec roughness is you look at last year's or the previous prints and then think, maybe I can tighten it up a little bit and it'll look better. Is that kind of what's still going on? Or? Nobody wants to admit it, not generally.
Specifically, that's how we do it.
Yeah, specifically. Well, I mean, so the previous part was working, then great. But how could you optimize it? How would you know? Because you may be, trying to speccing something much narrower than would work. There may be a bigger design space. It may be cheaper to manufacture if you knew better what you were doing or had a better parameter to describe it. Now, not always is sort of smoother better. Actually, this shows smoother is better, right? So we get up here higher performance, less roughness. So lots of times we think smoother is better. The other one was saying rougher is better. And it depends on what you're doing. If you're trying to provide good friction on a roadway, the rougher is better to a certain extent. And but if we're trying to provide good reflective surfaces, this would be the kind of relationship. But we also have performance relationships that go like this. For example, friction, where you've got capillary adhesion working, like on a hard drive. It used to be when you stopped your hard drive, your read-write head rested on the hard drive. And then so you actually had to roughen a portion of the hard drive so you'd have a landing zone where it wouldn't stick. And so because you wanted very smooth portions of the hard drive for recording data so you could have low flying height, but if it was that smooth, you'd have high friction. So this is the kind of relationship we're often looking at. And so historically, if you've been driving the roughness down here, and I think I got this upside down. We would like better performance up there. But all right, suppose this is friction coefficient, right? And we're going for a lower friction coefficient. And we get down here, so we've got a low friction coefficient. But if we get it smoother, we may raise the friction coefficient. This is true, for example, on a ski base. If you get a ski base too smooth, the friction goes up. All right, so we have this kind of relationship, and you could turn that over depending upon what you think you need. And so in these situations, we need a double-sided tolerance. So this would say the performance tolerance, say friction is there. But this is the kind of thing that we're trying to work on. So this is an actual valve seat, and we can see some mixture of, it looks like grain sticking up here, and there's the polishing marks. And so we're trying to make a seal across this kind of surface. And basically all of the manufacturing things, anything we do to modify a piece modifies the surface. And so this ends up being a highly coupled thing, and I'll be talking about that more tomorrow. How do we independently control surface finish and form on things, and microstructure and residual stresses? So this ends up being quite a complicated problem. So here's the kind of relationship we have between manufacturing and roughness. So if we have an abrasive process, RZ, the peak to valley roughness, will be equal to some function of the force divided by the hardness, the 1/2, and then some sort of shape factor here. And then we can't ever get things perfectly smooth by this process. There always seems to be something. So this is kind of experimentally based. Usually a kink in these curves here too. And so this would apply, of course, not only to engineering, but if you're looking at scratches on teeth, something that same sort of relationship should be holding. Let's take a little look at machining by turning. So we're scraping a chip off here on a cylinder, and that leaves a little surface. And so if we imagine that the tool is moving along in this direction, and this is what we would call the feed direction, and the workpiece is spinning like this, we leave a kind of helix down the workpiece, and if we take a cross-section through that, it looks like a series of cusps that should be like the tool nose. Now this is the conventional theory that everybody teaches for how to control roughness in machining. So you can work through the geometry, it's not that hard. I might have that on the next slide actually, but so the peak to valley roughness here, RZ, is going to be the feed square divided by 8 times the nose radius. And how do we work that out? Interestingly enough, we're talking about roughness. This is worked out with pure Euclidean geometry. And we see that, but inside these little tooth marks are things that we're not working out. But interestingly enough, and we can see Claire's poster this evening. So Professor Latigue from Cache they've been doing better modeling on what's happening inside these on something even more complicated, because I didn't dare try milling, and they're doing milling. So we can see some effects of milling. So please visit her poster and see some more details on that. Oh yeah, here's the simple little derivation on this thing for figuring out the peak to valley roughness, RT or RZ. There's subtle differences. Let's not worry about that now. But this is all Euclidean kind of calculations. And if you actually try to do the experiment, I just took this from an undergraduate lab, and this is kind of extreme scatter. Here's the theoretical curves, and here's what was measured in the lab. I think somebody must have thrown their notebook on the table while they were making the measurements. But anyway, and that's what we were looking at before. And so here are the little cusps that, and here's the inside, just to remind you what that looks like. But not all the surfaces are turned. So here's a surface that we took, and this was ground and abrasively polished. So we see the abrasive processing marks here. And so it's got a strong directionality or anisotropy to it. And then it gets thrown in a tumbler, kind of like a washing machine with abrasive in it. And this is made by Bel Air. And I recycled this slide. I used this slide at IMTS. So had you been at IMTS a month ago, you could have found Bel Air at this location in Chicago in the exhibit hall. But Bel Air is actually run by a WPI grad down in North Kingston, Rhode Island. But it's interesting to see the way this process evolves in this sort of mass finishing to get a non-directional surface. And it looks like to me, it looks like a pile of lawn clippings here with all the nice little things. And it gives a very nice matte finish and takes off some of the burrs, as we can see here. So this is a part we did in the lab, and I'll be talking more about this tomorrow. So one of the interesting things about geometric properties of surfaces is that they change with scale. But here's this is taken with our Olympus. So this has been measured with our Olympus confocal microscope. And so this is an edge that we honed in. So this is sort of the best finishing job we could do on this aluminum edge without going to fine scale, metallographic polishing. And then we put it in the mass finishing machine. So you can see the way that takes the edge off. And we'll be talking more about this series of things as we look at radius as a function of scale. Conventionally, surfaces are measured with stylus instruments, and so and we exaggerate the vertical scale compared to the horizontal scale, because otherwise it looks like Kansas, and we really like things more like the Rockies, right? So we've got these big dips through here, or the Andes, right? And so here's the round nose of the tool, and then this other stuff is the non-Euclidean part. Now, as I said, often we see that the waviness cutoff is not spec'd. Sometimes it's because the part is too small to actually get a measurement that long. But so here is the trace that's leveled, then here is the waviness that gets taken out. And then, so this gets down to the roughness, and then everybody can kind of agree, oh yeah, this is roughness because we've gotten this longer wavelength out. But what exactly should this cutoff be? Here it's 0.8 of a millimeter, but from the, let's see, why do I have 0.8 there twice? Well, I'll show you more, but oh yeah, this, all right, so there's the waviness and there's the roughness with the cutoff between waviness and roughness. Now the form is already taken out of this thing here. So there's the waviness to roughness cutoff at 0.8 of a millimeter. If I heard someplace historically, this is important because in Germany, some first roughness measurements were made through a microscope, and the microscope had a field of view of 0.8 of a millimeter. So that was what got to be the cutoff for roughness, because that was the way somebody started measuring it. The basic height parameters that we see most often are RA, I already mentioned that, RT, peak to valley. This is over smaller segments, and the RZ is over the whole length. So you'll see me interchanging on peak to valley RT and RZ. But then you can have the peak height and the valley depth, and that's taken from the mean line, essentially where we filtered out the waviness. So there's the mean line. And so this allows us, RP and RV allows us to tell sort of peaky surfaces that would be good for abrasion or friction from surfaces that have got more valleys, and is good for, say, low friction, so you can get wear debris out of the interface and have lubricant stored. Just to emphasize the importance of specifying the cutoff. So this is probably the cutoff you should be using on this one. But let's suppose you dropped it down to 1/4 of a millimeter instead. What happens to the RA? Well, the RA goes from 3.4 to 2.4, a 41% change. So if the designer hasn't spec'd the waviness cutoff, and you're not meeting the spec with a 0.8 millimeter filter, and it's time to go home, change the filter to 0.25, see, and then the parts will pass, and then you can get out of there, right? It's actually not what you should do. You should be finding out what the right cutoff would be to use. But so this definition, what scale does roughness start, has a profound effect on the results, and these are the conventional height parameters. And there's different choices on filters here in the. Now here's an example, and this comes from Nanotech Systems up in Keene, New Hampshire. So this is electroless nickel plated on, I don't know what they have for a substrate. And this has been diamond turned and faced, and then these grooves have been put on it in the X and Y direction. And these colors that are coming off, some of you may recognize this effect. This is not pigment, this is not painted blue here, but this is a result of constructive and destructive interference of the waves, the light being reflected off the surface. And you get this when you've got very consistent kinds of scratches or marks or grooves on a surface that are consistently spaced long enough so you can resolve them with your eye. And you can see here, this is a nice blue coming off a very long length of this thing. There's some green there from this. So this was first faced Anyway, let's take a more detailed look at this. So here in a scanning electron microscope is the cross where those two things come together. And we can see this is made up of 500 nanometer grooves. If we look at the scale here, there's 1 micrometer. So these were done with a diamond tool, very regular, coming across this whole thing and meeting up so well in the middle. So this was a kind of show-off piece for more. And it's down in here. We can see the little burrs that were created, by the chip formation at these very fine scales. Electroless nickel is amorphous, so we're not struggling with grains or other things. Here's another very fine part. Actually, I took this picture in the lab in Annecy at the Université de Savoie, so I need to check and see. Oh yeah, Gaetan and Hugues are here, so they may recognize this. But thinking about scale, so this is a watch part. This is on somebody's fingertip. You can see the fingerprint things there. These are bearings. So as we get smaller and smaller parts, where is the roughness and at what scale do we have the roughness? And if you need to take the roughness in here, obviously you're not going to get up to 0.8 of a millimeter. So this waviness cutoff thing is often problematic. So here's another thing from Nanotech Systems. There's more tools, and here's one of their, so the business into one of their machines. This is some grinding that's being done to get a very smooth surface. This is the mold for the lens on your cell phone camera, which is aspheric lens and has tolerances down in the nanometers, tens of nanometers. And you see it's reflecting the corner of this, the ceiling and the walls here in the lab where I took the picture. There's a millimeter scale in the background. So there's that's the reason you can have all of these lenses on your cell phone camera so cheaply, is that you can make a nice tool. There's 3 companies, if I understand right, that can make the tools that'll make this part. 2 are in Keene, and 1 is in Japan. Now the funny thing about this from a roughness standpoint is that we're trying to make these very fine, very Euclidean, very smooth surfaces, and what are we using? Basically kind of broken rocks glued together and a distinctly chaotic geometry. So here's abrasives, and just for our visitors, this idea of taking little broken chunks of rock, like sand, and gluing it together in something like a century and a half ago pottery, was an idea that Higgins took from the Washburn shops and went down and bought a pottery called Norton and started making grinding wheels that 20 years ago was acquired by Saint-Gobain. But this is the way we started off making things. Some cave person picks a rock up off the floor and starts sharpening a piece of antler or something with it. And so we're still there. So for you people that are studying, stone tools and, sort of looking at this, we haven't advanced in some ways that far. So this is actually, this very nice image was put together by Kai-Si Wang and Shu Su. Are they? I don't know if they're here. This is actually 10 by 10 stitched together, and each 10 by 10 images stitched together. This is true color, so you can see what the abrasive actually looks like. One of the problems that some of us will be talking about, and we have some posters on as well, are these spiky things here that mess up the measurements. So this is made by stitching 10 by 10 together. Each of these has got over 1 million elevations. So we've got over 100 million elevations to make this image. This speaks to the richness of the kind of data that we have to work with now. I mean, 20 years ago when I came here, just over 20 years ago to WPI, we were happy. We'd get 200 by 200, and then we would have a lot of trouble working on it because you needed special processors to handle all of those that much data, 400 heights, and now we've got 100 million. So, all right, no surprise to anybody. Computers have come a long way. There it is in true color. And you can see sort of the stitching effect. So obviously this could get better. But and here they are. There's Kai-Si and Sue. All right, so back to some more general things. So we have some process that creates the surface, and it may have some chaotic components itself. And then this surface, and at a fine scale, they all seem to have this kind of jumbly appearance, influences the behavior. And so then the surface metrology is measure and analyze this. Now, surface metrology is not a term that's all that well known. About 15 years ago, I think we sent a proposal into the National Science Foundation, and they said, we were glad to receive your proposal on surface meteorology, which made me quickly run to the proposal to make sure my spell check hadn't fixed that for me. No, it hadn't. So, and then the funny thing was, and this rarely happens with me in the National Science Foundation, they funded it. No, I don't know if, and maybe that's why they haven't funded anymore. We were expecting something about thunderstorms. But anyway. So what we want to be able to do, though, is be able to link the surface with the way it was made and its behavior, so we can discriminate surfaces that are either good or bad, and correlate with, you know, how they were made or how they're going to behave. Or, you know, we may be discriminating, and then there's Tracy here. So we had a graduate student coming in from BU, and she is looking at the differences between teeth from eastern and western Tennessee from about 2,000 years ago to see if they might have had different diets. So the discrimination has roles in forensics. And tomorrow we'll have Nick Petrecco here talking about trying to figure out who shot who, or, you know, well, he's going into some of the statistics on that. Now, the thing that makes this really challenging, I'm sure you've figured this out by now, is this is not a Euclidean surface, so we can't define it in normal Euclidean ways. And one way to think about this is if I have a cylinder, and I say it's a cylinder, and here's the diameter, here's the length of the cylinder, and here are 3 points on the cylinder, you can tell, if it's Euclidean, you can tell me exactly where every other point is on that cylinder. Right, so if it's Euclidean. If it's chaotic, I can tell you where 1,000,000 points are, and I can go right in the middle of it and say, now where's that point supposed to be? What's that height supposed to be? And you can't tell me exactly, sometimes statistically. But, and so that's sort of what I'm calling geometric chaos. All right, so as we talked about, and we mentioned there's the trend in manufacturing is let's push the Euclidean geometry down to finer scales. Let's get greater control over it. And then let's get more sophisticated about measuring and analyzing, and that's some of the work we've been doing here, particularly on the analyzing part. And the better we can understand the process and the tool workpiece interactions, and then the surface performance after that, the better we can spec and manufacture things. All right, so let's take some look at the measurement issues. This is a particularly challenging piece to measure. It's a tool that's used in chemical mechanical polishing. It's used to condition, I think, the tool that actually is used on the wafer. The thing here is that you've got these pockets in that are supposed to retain slurry in the process, and so these tend to be very steep things, and we'll see some of the difficulties in measuring that. But all right, so we start off with the surface or a replica of the surface, because often we can't get into where we want to be, or it's like a runway or something, and we can't sort of hold up the flights while we do our measurements. So we work on a replica. And often the characterization analysis is in the instrument, but you could get separate software too. One of our longtime supporters for the lab and for these conferences is Digital Surf, who makes their independent software in Besançon, France, Mountains Map. Anyway, so you may do the analysis in the instrument or apart from the instrument. And then what are we looking for? Well, in engineering, we're trying to add value, reduce waste. There are lots of interesting scientific questions. What is the right scale for heat transfer, for example? I don't think anybody knows exactly how to do that. Of course, there'll be lots depending on the fluids or something involved, how fast they're flowing. But for design, quality assurance, process control, We should add forensics. And now, so the key thing, though, in all of this is, can we discriminate and correlate? And I'll be talking more about that. This is where the value is added in surface metrology. Somebody comes in and says, these two surfaces are performing differently. They have the same RA. I don't know how to tell them apart in quality assurance, but so how do we do that? So that's, if you can discriminate those, then you've added some value to this. And somebody says, well, geez, how do I design this? These things we were looking at before. So how do I know how I'm in the optimum range? How do I know I'm not defining my tolerance too narrowly? Is there a larger tolerance we could use? So that's, we learned from the correlation. So as we know from Lord Kelvin, measuring is the key here, and getting a number on it. So we've made a lot of advances in measuring surfaces, and so I think the challenge really is figuring out how to quantify it. How are we going to do our numerical reckoning? And here's the challenge. So here's a surface that we measured in the lab, and you can. So how are we going to put a number on this kind of surface that's going to correlate with behavior or tell us something about the way it's made? And as we zoom in on it, we see that it maintains its roughness down to a fairly fine scale, and we really don't know if these smoother things here are just because the measurement instrument isn't resolving something in there, or if it's actually smoother there. So, all right, so let's take a look at profiles and surfaces, contact versus optical, see if we can tell a good measurement from a bad one. So historically, and this is still what's used in industry, and it's still a very important instrument, and it's this the profiler, and we're grateful to MAR for their support. So what we're doing here is we're checking the tip on this, and the way you do it is you put a razor blade in a clamp and you run this thing over a razor blade. And so here's sort of the business end, and so you can actually see the tip reflected here. So the idea is to have a very small tip with a light force on this that goes across the surface and measures a profile. And we saw that already. So if we take a look at this schematically, you have a spherical tip and usually 1 to 10 someplace micrometers, usually 1, 5, or 10. Some normal force holding it down. Now this is an older MAR instrument that I had in Switzerland. So you need to hold it onto the surface. So you've got some finite contact stress here, which is important. And this was this thing here with this sampling interval. So the sampling interval is the distance between the heights. We'll see more about that in a moment. Vertical resolution, tracing length. All right, so this is the way roughness has been done since about the 1930s. Now, as I said, there's a finite contact stress. So this is a scanning electron micrograph. I don't know how I keep doing that. There we go. So this is a scanning electron micrograph, and we can see here's where the stylus went across the surface. So one of the challenges is knowing what kind of measurement instrument is the right one for your application. So this is an aircraft aluminum alloy. We did fatigue tests on this, and these little marks here are where iron-rich intermetallics or primary silicon particles were dragged along with the tool. So here's the ridge between two feeds of the tool. And these little marks in our fatigue tests were often where fatigue cracks were starting. Now the problem with measuring this and trying to make a prediction about fatigue crack initiation as a function of roughness, if I've used this stylus instrument, is that I can't measure those things, right? I'm not getting the bottom of the valleys, I'm breaking off the tops, but I'm still getting a valuable measurement in many respects. And the question is, how do we know sort of what the limits are on all the different instruments? All the instruments have different sort of limits on their resolution. So here's one that we're grateful to Solarius for. It's a UBM that's been discontinued quite a while ago, but it still runs well. Nice metrology frame with 2 XY tables and then some kind of measurement head, and there's different ones that we bolt on here. So this is a horizontal scanning. Here's another one that we made with the support of NASA Langley for studying runways for the space shuttle, set up in a lab configuration. When we go onto the runways, these end up here to scan the scanner over the runway, which is a lot easier than scanning the runway underneath the the height measurement device. And then we're grateful to Olympus, and this is the older one, the Lex 3100, shown in the lab. And that's a vertical scanning instrument. I'm not going to get into all of the details on these. So anyway, the geometry, the Finescale is roughness, as we were discussing. And then in between is waviness. And so let's take a look at the difference between the two. So here is a schematic of the way you take a look at the tip on the stylus. So the idea is we'll get a razor blade that's sharper than the tip. So when we run the tip over the razor blade, instead of imaging the razor blade, we're actually going to image the stylus tip. And so you can kind of see how that works out. If I get a tinier radius here, this thing moves up and down over this, and instead of using the stylus to measure the surface, I'm now essentially using the surface to measure the stylus. So that's the old standard way of doing it, and we were talking about this about a year ago, and we had a student here, Florian Aufort from France, and and I said, you know what, Florian, let's just take the stylus off and let's put it under the Olympus and measure it. So here's the stylus tip, and now we'll just measure it using the Olympus. And how's that going to come out? Well, it came out pretty well. So a replacement for the razor blade test, if you happen to have a nice Olympus confocal microscope, is here. And then, so how does the radius difference come out? Well, we're within some tens of nanometers of being measuring the same radius with the two methods, so that looks pretty good. We might not have taken the same cross section there. I'm not sure if we knew exactly what the orientation was, but in any event, so we come up with about the same thing, which tells us, you know what, I guess these agree well. So if we're comfortable with this, we're comfortable with this, and vice versa. Then we go on to the piece. Now the last thing we saw the trace was scanning electron micrograph. So this is the trace measured with the Olympus, and it's stitched together. You can kind of see the stitching so we can get the whole trace length. You can see a little sort of T on the end of this. This is where it starts or stops and goes across. And if we zoom in on this, we can see that the stylus is, it's not perfectly stiff in the sense parallel or perpendicular where it's tracing. So you can see it kind of wiggles through the piece there, which is a little bit scary when you like to think, oh no, this isn't, this is measuring the actual surface. But all measurement instruments have some things like this. So we can take a look at how deep is this valley, and it's not that deep, right? It's a few tens of nanometers deep that the scratch is made here. And so this may be so far outside of our tolerance, lots and lots of parts it is, that we don't worry about that. And it's kind of interesting to see, all right, here is the surface roughness and the stylus radius at the same scale. So somebody talked about using the stylus is like rolling the basketball down your driveway to measure the roughness on the driveway. But as I said, there's plenty of useful information that comes out of the stylus tip. But it's an interesting image to keep in mind. And there's Florent. And so then we went back to this same surface and we said, well, what kind of indentation do we expect based on the hardness? So here's a micro hardness test measured with the Olympus. Now you can see the pile up around the edge. And there's some work that could be done here to look at, for example, work hardening using 3D measurements. Because as I push the stylus in, if I get pile up very close to the indentation, that means it doesn't work harden very much. If the pile up extends out away from the indentation, that means the material next to the indentation work hardened, gets stiffer, and transferred the load further away. So if I combine a hardness test with a 3D measurement, I can actually learn more about the material behavior. This might be useful in taking a look at, say, machinability and things. Now here's something we don't often think about too. So we were looking at the stylus, but with all the optical instruments and non-contact instruments, we don't measure the height at a point. I don't know if I have that on there. It's impossible to know the height at a point. if we think of a point mathematically. So if, a mathematical point's infinitesimally small, given the inherent nature of matter as being sort of electrons and nuclei. If I have an infinitesimally small point and I try to poke the surface with it, chances are it's going to miss everything, right? And so the height at a point tends not to have so much meaning in the mathematical sense if I think about sort of real materials. So when I measure the height or sample the height on a surface in surface metrology, I need to imagine that I'm doing this over some sampling zone. So, and inside that zone are variations in height. So I don't know the height at a point, but I know something about the height in a sampling zone. And we could do some work on this, and we could do it with the Olympus. We just haven't had time, and I see some of the students working in the lab are here, so this could make us think of projects where we would use different magnifications or combine optical with atomic force, and we'll look at it momentarily, to see, well, what is the height inside? Because when you say, all right, I shine a laser, often we're using a laser, right, to measure the surface height on the surface and get some interaction with the surface, get the information back. It's over some zone. Inside that zone, have I got the highest point in that zone, the lowest point in that zone? Have I got some arithmetical average? Is it a weighted average? I suspect it's probably a weighted average, more towards the center or something. But there's a sampling zone. Now the sampling interval is how far do I move over before I measure the next height. Now I can oftentimes adjust the sampling interval, so that's an adjustable kind of thing. But the sampling zone I'm kind of stuck with. And as far as I know, and I don't know if anybody else knows about this, has anybody done research on trying to establish what the sampling zone is and know more about that? Because I haven't seen anything on that. And so we can think about different kinds of overlaps between the sampling interval and the sampling zone. Maybe they come together nicely like this. Actually, Stefan Scherer upstairs, who's here with Alacona, said that he thinks this is more what's going on in most instruments, is that there's a fair amount of overlap. The sampling zone leaks over into the adjacent sampling zones. But on adjustable instruments, certainly you can have this kind of thing too. That's just often not considered. Let's go back to one of my favorite parts here. And we saw that already. So here it is. Now this is interesting. This is measured with the Olympus. These are 500 nanometer ridges. And I wish Nancy were here because she's the physicist. But so these are 500 nanometer ridges. And if we take a look at Sparrow's criterion, or the Raleigh criterion, we see that the resolution should be wavelength divided by about 2 times the numerical aperture. Well, the numerical aperture is 0.95 with a 100 micrometer lens. We've pushed this with the 8 times zoom. The wavelength of the laser we're using is 405. So the resolution should be about 213 nanometers. These ridges are 500 nanometers apart. Now our sampling interval in this case was just about 4 nanometers, so well below the Raleigh or Sperry criterion. So it's interesting that I think we get an image at all because of the physical limits of the light, and that we can see so much detail on this. Not only do we have a pretty good idea that these are ridges, but we can see the burrs and we can see some of the interaction. Now, of course, the SEM, why don't we use the SEM for measuring everything? Because, wow, that looks so much clearer. Well, we don't get heights out of this very easily. And here we get all the heights. We can also see, this is very smooth, but we can see the facing marks. You see these concentric rings here. So this was first faced, and then it had this groove put in. And now we can look at this in 3D, and we can actually see, and we cut off the vertical. Here's the vertical. So there's 3.5 nanometers, or vertically, is that what we've got? Yeah, 3.5 and 7 nanometers vertically as we go up here. And so we've got a vertical scale on this. I'm sorry, micrometers, not nanometers. Micrometers and X and Y. So we have a real measurement that we can do something with, unlike the SEM, which gives us an image. So as we zoom in on this, we can see the need to actually do some kind of spike filtering in here, because these points obviously are not real. These are some sort of, we can call them doubtful measurements, aberrant points, spikes. If they go down, we might call them dropouts. We can also see, here's the feed as it went in. You can see the sides of this. All right, so I thought I'd say a couple words about AFM. And so this is the way we extend our measurement to very fine scales. So use some sort of tip, might be a diamond, might be silicone is commonly used. And these are some of the older ones that go back almost to, I guess somebody got a Nobel Prize on this out of Zurich many years ago. But here is a very small image size, 2.5 by 2.5 nanometers. And this is graphite, so we're seeing atoms here, and then we see something that's stuck onto this sorbic acid. So, so it is possible to do these resolutions at very fine scales. This does give us height by height measurements, but it's, we're still at a state where we don't do a good job at comparing from different instruments, or often different lenses on the same instrument. So there's Dr. Stedman who proposed this kind of way of comparing different instruments. So let's put the vertical range here, so we go from the resolution to the maximum it can measure, and we'll do the same thing with the horizontal or spatial here, and so that gives us a way of comparing instruments. And I don't know who, digital instruments, I guess, put this one together. They talk about optical here stopping at 1 micrometer, but we clearly saw 500 nanometer features a moment ago with an optical instrument. So anyway, so there's Dr. Stedman, who thought of this diagram. All right, so we have the same issues too when we measure surfaces we do with anything else. We get accuracy, precision, trueness. Often though, when we're looking for precision, so repeatability and reproducibility, we're looking at the parameters like RA. So how well does our characterization of this repeat from one to another, as opposed to how well did our height measurement repeat. So if we look at the repeatability of individual height measurements, so we can take first and second and plot them against each other, if it were perfectly repeatable, we would get an R squared of 1, and this would be 1, and that would be 0. But as we do a best fit line through this thing, we can see it's not perfectly repeatable. They all fit on this line. So, so this is something that is not often done. I don't know, how many people here have just taken two measurements and compared them like this without moving anything? So a couple people have. How many people here now think maybe they should have done that? Nobody. If I haven't convinced anybody this is a good idea that didn't already try it. So how repeatable are the measurements? How repeatably can I come back and measure the height at the same location? So I think it's a fundamental question on this. Anyway, so what are the trends that we have in measuring? So there's more optical over contact stylus, but the contact stylus, as I said, is still very valuable. We're getting more sophisticated in the analysis, and I'll talk about that in a moment, and looking at the texture interactions. So the third part of this is let's take a look at the topography, the analysis of the topography. And here we get into this thing about these images are beautiful images. A nice image is worth 1,000 words, but I'm an engineer, not a poet. I want a number. So we can enjoy the 1,000 words some other time, but I got to get some work done. So we've already taken some look at the characterization parameters, but let's take a look at some of this discrimination. How do we do it, and then kind of what's next. So the height parameters, RA is the arithmetic average. So we take the absolute value of the heights about the mean line. So you have to do the absolute value, because if we get the mean line in the right place, these would be negative, these would be positive, we'd add them all up and we'd get 0 all the time, and that wouldn't be very useful. So we'll take the absolute value. Or we could do the root mean square in this way, and this, once we subtract the mean, which we've done here, because that's what this line does, as we subtract the mean, this is then essentially the standard deviation. Now S is if it's for a surface, so heights is a function of x and y, and R is if it's for a profile. Heights is just a function of x, and that's what we're showing here. Now, one of the obvious things is if we're trying to use this to discriminate good and bad surfaces or design surfaces, one big mountain and the average can have the same average as two little mountains or two little valleys, because we've taken the absolute value or squared it. So we can easily imagine that all these surfaces would have different behaviors So which one would you rather sit on, or which one would you rather use for grinding, or inside of a cylinder, or something like that. So the RA isn't going to be good at discriminating those things. So some of the other things we can look at, though, if we take a look at peak height, for example, and we could compare, say, the peak height to the RT, peak to valley, then we could start distinguishing those surfaces that tended to be, be dominated by peaks or valleys, or that were even, right? So here's the kinds of things that we're trying to characterize. So here's another exercise now. The other one was a stylus where we looked at what happens if we change the wavelength. So here's a wavelength in micrometers on this 3D image that was made, or 3D measurement that was made with this 10 by 10 tiling. Look what happens to the RA when we change the filter. It goes from 19 to 0.2. And with no filtering, it's 26. So profound effects. So the filtering makes a big difference in how we evaluate this clearly. So those are all height parameters. There are spatial parameters. They become a little bit tougher because we want to define crossings or something, or peaks. How far apart are the peaks? And there's an interesting sort of notion of scale that's inherent in this too. So this is one of the questions I like to ask the students. Where's the highest point in New England? Anybody know? Anybody here from New England? Where's the highest point in New England?
Washington.
And you know how this is going to go, right? Because you were in class the other day. All right. So don't give it away. So where's the second highest point in New England?
Washington.
Yeah, that's right. That's right. You got it. All right. So what you try to do is lead the students into thinking that, all right, the second highest point. Oh, it was at the Mount Adams. It must be in the presidentials because the second highest point, Mount Adams, or is it Liberty or Lafayette? And then you go, no, it turns out the second highest point in New England is right next to the highest point. And this whole idea of a summit has got some scale, because somebody says, oh, no, it's not the same highest point, it's going to go down and then up. And I go, well, I bet on that rock on the top of Mount Washington, there's plenty of ups and downs, so you could define probably millions of summits that will fit all underneath your boot when you get up there to the top. Now, the thing is that we're not going to issue you a million patches to put on your pack or something that you scaled all these peaks, because there's a notion of scale. And not only, we're not going to give you another one for just climbing down and going up Boots Spur, you need to do some hiking before you get over to Liberty or Lafayette or the Flume or Adams or whatever the second one is, before you merit scaling another peak. So the whole idea of peak has got some scale notion in it. And so that's the problem with these, is that I've got to define, how many crossings do I have, or what is a real peak, how far back up does it go, and so it gets a little more complicated. So here's an interesting thing to think about too, particularly if you're using double-sided tolerances, and if you're using more than one parameter to spec a surface. And it's the same thing that we run into when we're specing geometry on a surface. We often say, well, plus or minus something in two directions, and we do a rectangular tolerance. Now, when you do a rectangular tolerance, are the corners good, or is the tolerance really more circular or oval or something? And if the corners are good, why wouldn't this part out here be good? And then but here's our manufacturing range. Might all be good if this diagonal here is okay all the way along there. Why don't I take the same distance this way and call that good too? So there's some things to think about as we spec surfaces. This might be what's functionally acceptable, and we're leaving some stuff out by this tolerance. That's kind of the point. So how well are we speccing things? Here's a little thing too on the surface. So let's suppose we've got a sine wave. All right, so we've got a nice long wavelength here, and so let's calculate the RT and the RA and the RQ. You can do this easily in Excel. So let's take it at a smaller scale. So here's a little sine wave, and we can calculate the RT, RA, and RQ. Now, So we might imagine that these are going to be interacting with things in different ways. For example, if I'm hiking, this might be something that I'm going to turn an ankle on, and this might be something that gives me a nice grip. On a road, this might be something where the tire bumps through it, and this might be something that's giving us good traction. Or this might be something that's scattering light, right? And this might be something that's actually looking shiny but just a little bit wavy. So we could imagine different scales of interaction for which these might be appropriate. So what happens if we add them together, and what happens to the parameters? So if I take this blue one and add it to the green one, I get the red one. And then I'll calculate the RT, peak to valley, RA, and RQ for this. So the peak to valley goes from the green to the red. It gets a little bigger, right, because we got these things sticking over the end. But the RA, now this is used in like 90% or over 90% of industry for speccing things. Here's the interesting thing. The RA didn't budge. I've got exactly the same average roughness when I added the little stuff to the big stuff. And we can imagine that the green curve is going to have much different behavior than the red one, because the red one may be doing some light scattering, make it a matte finish if I'm looking at photographic paper. So it tells us something about the limits of using RA. RA cannot tell the difference, or cannot discriminate this red thing with all the waviness on it and the green thing. RQ can a little bit, but it's not great at it. All right, so here's something to think about. What would we like to spec in a surface? So I've been critical of the RA and the most commonly used one. Now, if RA works, right, you're producing good parts, your suppliers are happy, all right, stick with the RA. It's easy to do. Got a stylus, can measure it, terrific. If everything's going along like that, maybe you don't need to do anything else. But maybe you should be concerned, though, if your competitors are going to do something different and there's a different sort of space that you can be designing in which case, come see us. We'd be glad to work with you and try to learn more about your surfaces and figure out what kinds of instruments might be better. And one of the things that I've been working on since I started this at the Swiss Federal Institute of Technology in Lausanne almost 30 years ago is, all right, we've got high-speed digital computers. We thought they were high-speed 30 years ago, but they've gotten even better. Why are we using 1930s parameters? So the question that often we're still asking when we're looking at a part and saying, how are we going to spec it? And this may be a lot of reasons for this. We're saying, which 1930s parameter can I use to spec this surface? As opposed to, what would I really like to know about this surface in order to be able to describe how it's going to behave and discriminate it? So my contention is, I'll be developing this more in the tutorials that I'm giving tomorrow, is that there's really two things we'd like to be looking at. One is the geometrical nature of the features that we're characterizing, and the other is, as you might guess, the scale. How big are those features? And so some time ago, we started doing area. And so area comes up in all kinds of things. Now, in heat transfer, so we got Newton's law of cooling. So how fast we can cool something down depends on the surface area we have to lose heat over. Same with same with mass transfer. And so if we're trying to carburize something and try to get carbon into it, how much area do we have to put that in? The drying problem that Jamal talked about earlier this morning. We can think of some other things too that are probably more complicated. Current density. So we have some problems though there with the sharper the radii or something, we get greater field strengths. Load transfer, though, is really a question of area. How much area do I have to transfer this over? So if I'm smushing two surfaces together to make a seal, how much are they going to smush? And that is actually probably plays an important role in sealing things. So the compliance. And then we've done some work just in general, like adhesion, discrete interaction model. So how does adhesion strength work, and I'll talk more about this tomorrow as well. If I have a number of finite bonds, how many attachment points do I have? Or if I'm thinking about something like catalysis, how many interactions can I have on the surface per unit area? Now, the interesting thing is on the chaotic surface, right, we talked that roughness is often inherently chaotic. And if I think about a rough surface, the area is not unique. So this goes back to Lewis Fry Richardson stuff. How long is the coast of Britain? So the coast of Britain doesn't have a unique length. If I look at it at a closer and closer scale, I keep seeing more little bays and peninsulas that I didn't notice at a larger scale. And so how long is the coastline? Well, mathematically, we could describe it as being infinite, but practically there's some sort of limits. So when we started doing the 3D work, Richardson said, how long is the coast of Britain? And he was from Britain. So we sort of saying, well, how large is the surface of New England? There's this old joke about Vermont would be as big as Texas if you could flatten it out. And so the Vermonters are very proud of their hills. We actually tried to do this, and it turns out that if you flatten Vermont out in a computer, you've got to get to a scale of 10 to the minus 127th meters, which there isn't even a name for as far as I know. So you're into the subatomic or below subatomic particle size. Anyway, you can't flatten Vermont out and catch up with Texas, as it turns out. All right, but here's the problem. Which surface area do I take? There's lots of different surface areas depending upon how closely I look at something. So if I'm trying to calculate the heat transfer using Newton's equation, which has been around for 300 years, how do I measure the area? So what have we been doing traditionally? We measure Euclidean x, y, and we ignore the roughness on it. And then we put in some sort of fudge factor to take care of the roughness. So if I'm trying to look at heat transfer on a very fine scale, like in electrical components, what should I be thinking about there? Now, when the scale is not indicated, right, and we were talking about where's the problem of the filtering. So when the designer specs the filter, he says, all right, this is the scale where I think roughness starts to be important. This is where we're going to start defining roughness. But when we actually look at a measured surface, what's the scale? Well, it's usually the scale, the sampling interval of the instrument. Now, for a long time, we've had in the ISO and in the US standards is the developed area. So if you've got a 3D measurement, we've got a parameter that's the developed area where you sort of triangulate and you measure from point to point on the surface, and you come up with an area that includes all your measured points. You compare that to the XY surface, that's the developed area. But that happens to be at the scale of the instrument, which is probably an arbitrary scale relative to the function. So how do we get around this arbitrariness? Yeah, we can do the area, but it's at some scale the instrument likes, which has got maybe nothing to do with the function or the way the surface is created. So tomorrow I'll be talking about some of that, how we can put that together. And that's what we developed, is this tiling exercise. We got a patent for that a number of years ago, which we've let expire. That's been in the ASME standard since 2002. It just came out in the ISO standard this spring, although they're slightly different, unfortunately, and that's something we need to work to correct to bring them in line. So here's another example of this virtual tiling. As these triangular tiles get smaller and smaller, the apparent area goes up and up. And the number of opportunities for interaction goes up. So what is roughness? Well, if I do that tiling exercise, and I'll talk more about this tomorrow, at the largest scale, and compare the tiled area, so when I put these tiles over it, right, I get so many patches or tiles, and here's the size of the tile going down and down, getting smaller and smaller. And the relative area is the ratio between the measured area, which is 18 patches times this, divided by the conventional Euclidean or XY area, projected area. So as I go down to finer and finer scales, you can see the relative area goes up. So at this scale, I've got 50% more surface to work with than a perfectly smooth surface, almost 51%. That's what that's telling me there. But which one do I choose? Which is the right scale? So here again, we see the same kind of thing. Here's the scale, number of tiles. And then, so we can plot the relative area versus the scale. So this is the size of the triangular tile. This is the area compared with the projected area. So on this particular surface, it's only getting up to like 17%. And so we can divide this up. This looks like a good way of defining the roughness, because when it's form out here, the triangles are so big they're insensitive to the topographic details. Then we've got this part here where we can actually fit a pretty good line to this on lots of surfaces. So this is sort of the roughness. And then in between, this transition region might be the waviness. But anyway, so there's a way of thinking about it, and I'll talk more about that tomorrow. So who decides? Well, it depends. The designer in the spec, as we were talking about, who decides what roughness is? The metrologist, well, if I'm using a profiling instrument, or if I'm using a confocal or an alicona or something, this is a surface metrology instrument. I'm measuring roughness, so what I'm measuring must be roughness. So the metrologist kind of gets to decide. And then in manufacturing, well, if we can hold sort of close to Euclidean geometry, then maybe that's not roughness. But if it's at the scale that we usually call roughness and measure with roughness, is that roughness? And then how well did the designer know what they're speccing? So what is roughness? What do you want it to be?
So is there any implication that there are different kinds of mathematical models that are used for each of these categories, roughness, waviness, and form? Like waviness to me suggests periodicity. Is that typically used, or can you use a statistical measure of waviness?
Actually, the periodicity is something where that language is working its way into the ISO standards. And so the waviness would have some periodicity to it.
So then form is Euclidean?
Form would be Euclidean, yes, smooth.
Is periodic, and roughness
Is aperiodic, yeah. So that would be one way of defining as well. Yeah, very good point. Thank you, Jim. Actually, a neat way is this modal analysis that Gaetan and Hugues will be talking about tomorrow. And they actually have some nice software for filtering out the spikes. So that, I think, has a lot of promise. One of the nice things about the modal, if I've got this right, is that you can go right up to the edges of what you're measuring. Is that right? Yeah. Whereas with other filters, there's a border there that you have to, that you can't filter because you need a sample exposure. So I think theirs has a lot of promise, and they'll be showing people how to use that tomorrow. Thank you for that question. Anyway, thank you for your attention. And we've got some time for some more questions, if you like. Good. Yeah, please.
So I'm really interested in how stuff looks, okay? And so I'm trying to make a connection between the different categories of form, waviness, and roughness in mechanical terms to appearance, right? And so when I'm thinking about appearance, at the finest scale, we have surface reflectance, or something like gloss or BRDF, or some kind of, right? In the middle, there's texture, which is visible deviations, but it may or may not be periodic, right? It could be a statistical. Right. And then we have form or shape. So I wonder, is it necessary, or are you always interested in periodic stuff going on in the waviness scale, or can it also be?
Could it be aperiodic? Well, I think it can be, certainly the way in the ASTM standard, at least in my view. What would you say, Ed?
I would think waviness can be aperiodic.
Yeah.
That's what it depends on wherever you set your cutoff, that's where waviness is.
There you go. So it's up to the designer to say, yeah. But Jim is from RIT, and so this is Rochester. So this is a big center for doing stuff to paper. So is it shiny? Is it matte? Is the matte finish directional? And so it's interesting too, because the way Jim uses the word texture, I think is from the paper kinds of things. Whereas texture, ASME B46, is roughness, waviness, and lay, is all texture. If you,
Texture is the carpet too. There's texture there.
Yeah.
This is a texture. So.
Yeah, the civil engineers, for looking at roads, roughness is what makes the ride uncomfortable, bouncing around, that's roughness. Then you've got texture, which is providing the friction, and microtexture, which is the fine end of the friction.
Just one question. I'm not used to your definition of Euclidean, probably because I'm not a mechanical engineer. But the surface of a sphere is non-Euclidean. But you would call it here Euclidean, would you?
Yeah, and thank you, Lars, because I'm certain in certain circles I'm misusing this term, but I'm using it to mean a surface that if I magnify it, it always stays smooth. So I can define it with equations. So how would you define
Well, I would
Euclidean?
define smooth surface as basically a form of entropy, basically. Because, the mathematical definition of a Euclidean surface is that you can, if you have a line in one point outside, you can draw a parallel line to the other one, which you can't on the surface of a sphere.
Uh-huh.
So mathematically, it's
I see. So,
totally different.
okay. I have perhaps not been rigorous enough. So what would you call the surfaces that I'm calling Euclidean?
Well, smoothness would be mathematical.
Just smooth. Yeah.
Smooth or entropy.
Entropy.
Entropy, yes.
Entropy.
Yes.
Because I kind of think of the chaos as being entropy. In other words, because it characterizes the amount of uncertainty that I would have in trying to choose that
More or
point.
less entropy.
So less entropy. Yeah, because, and what's the probability that I choose the right point in between two known points could be k log w.
Or smoothness.
Yeah, how many possible states do I have? So you would describe the smoothness as lack of entropy.
Yeah, we call it smooth.
Smooth, yeah.
I was just thinking, high school geometry, right? So ellipses and circles and triangles and rectangles.
Yeah. Well, this is the American version, I guess, of mathematics that we learned in junior high school, and Lars is bringing us a more global view. So, great. Well, that's neat. I'll have to think about rewording this, or at least because I like that explanation relating to entropy, because it fits with the uncertainty of being able to find the intermediate points. Anything else?
I was interested in the scaling exercise with tiling. Since industry is still stuck in 2D and will be for a long time, just cost.
Yeah.
Do you think it should work in 2D, I would think, especially for the isotropic surface instead of 3D?
Oh, yeah. So we do length scale analysis. I'll talk a little bit more about that. The length scale in itself is interesting because if I'm trying to find anisotropy or directionality on a surface, then I can use I can look at profiles in different directions. And in industry, if the profiling in RA is working, and you're able to make good parts and ship good parts, and the customer's happy, and then this is what you should be using. And it might be good to have something behind it so that maybe more about what's going on. I know when I was working at Atlas Copco before I came to WPI, they were trying to get coatings to stick to a compressor element, and everything was going along fine until they tried to get a robot to prepare the surface with grit blasting. And the RA was fine, but the surface wasn't. and the stuff didn't stick. So there is something to the, some value to knowing more about the surface, even if you're just using a profiler, to say, all right, I know what I might get out of the regime where I'm safe with a profiler. So.
Yeah, you can always get the RA if you want to change how you process the surface. And you stuff in this.
Yeah. But that was exactly the intent of RA in the beginning, was let's just use it to see if something's changed. Now you could change something without changing the RA, but if the RA changes, something's changed, and that was the best you could do, all right, we can catch it. Laura.
So we do a lot of time series analysis, which is just a wiggle, it's a profile of, climate change or something, it's still some sort of profile. And when we classify it, we decompose it into different sorts of polynomials, like first order, second order, third order. Why don't they do that in surface roughness as a means for characterizing it?
They do.
They do, okay.
Yeah, and it's...
I mean, that's essentially what form waviness and roughness are, but it seems like there's another way to do it.
Well, yeah, the polynomial fits, and you can see, the guys from Digital Surf do that, and we use that a lot to take the form out. That's kind of our normal way of taking the form out.
So that would be like the first order, and then
You can go to whatever order you want, or the modal filters that Gaetan will be showing us tomorrow. So it's a mode just like a vibrating string, so you got first mode, second mode, third mode or something. I start getting confused after I get by third, but it's all hand waving. But that's kind of what order equation do we use? Yeah.
But how come the terminology hasn't been adapted to that, or is it still stuck in the 1930s? Or?
No, that's an excellent point. All right, so if you look at the ISO standards, they are all, they define all the parameters based on calculus. And I argue, no, you should be using discrete mathematics because we're using discrete points. And so there is one sort of track of thinking on this, is that everything is smooth if we go to a fine enough scale, or at least we can approximate it as being smooth. And therefore, we're going to define all our roughness parameters based on integrals and derivatives as if it were completely continuous and smooth. And here's another point, because the fractals are continuous but nowhere differentiable. So that was one way of defining a fractal. So the surface is continuous, but I can't take a derivative of it any place. However, in all the ISO standards, it's all integrals, as if we could eventually get a high enough order fit, and we would that would be our ultimate achievement. And there is also a kind of, maybe it's subconscious thinking, is that anything that doesn't really fit that is probably noise or instrument noise. There's another filter I didn't talk about that's the very finest wavelengths. It must certainly be noise because everything should be smooth, right? But I think smoothness is really an invention of people. And most things are rough. And it's just too difficult to think of things that aren't smooth. So.
And in the end, it's all quantized. So.
Exactly. That's the point I make too. That since 1900 we knew that nothing's continuous. It all bumps along on quanta. Well, it's break time. I'd love to continue the discussion. We'll have some opportunity tomorrow. I forgot to announce this morning, or did I? Anyway, Hassan Zawani won't be able to make it. He had death in the family, so I'm filling in for him. So, and I